right, so I had somebody ask me about finding the area between two curves with a no calculator sort of problem. And so I've got two examples I'm going to do. First one, we're looking at y equals sine of 2x compared to y equals 2 sine of x, and trying to find the area enclosed by those two curves. So what we're going to do is first going to set them equal to each other. I know they're both wiggly functions, and I just need to figure out where they are actually equal to each other. And so if I set sine of 2x equal to 2 sine of x, what I can do is use the angle addition formula, or the double angle formula right here, to express that in terms of sines and cosines. I forget the double angle formula. Just please look it up. You don't need to have it memorized. 2 sine of 2x becomes 2 sine of x cosine x. And over here we have 2 sine of x. Great. Okay, so what you can do is divide everything by 2 and then subtract so that your equation equals 0. And then factor out the common piece of sine of x. So you can see here it's sine of x times cosine and sine of x times -1. And so then there's two solutions where sine of x is equal to 0 or where cosine of x is equal to 1. Be careful, because a lot of people are tempted right here to divide both sides by sine of x. And if you divide both sides by something, you are assuming that it is not equal to 0. So I could have divided by sine at that step there and then just written a second situation, a second possibility is that sine of x equals 0. Or you can set it equal to 0 and factor. So sine is equal to 0 at angle 0, or pi, or 2 pi, etc., etc. And cosine of x is equal to 1 at 0 and 2 pi, and etc., etc. So what we have here is there's going to be an infinite number of intersections. They're going to intersect at every value, every integer multiple of pi. So then what we need to do is figure out who's on top and who's on bottom in between those. So I'm going to choose 0 and pi as my bounds of integration, because those are the first two places where they intersect. If I want to figure out who's on top and who's on bottom in that interval, I choose any number in between 0 and pi and plug it into both of them. So let's call this one the blue one, and then let's call this one the purple one. So if I do the blue one and I plug in, for example, pi over 2, I would be calculating sine of 2 times pi over 2. That's the sine of pi, which is equal to 0. If I do the purple one, I have 2 times the sine of pi over 2, which is equal to 2. So I know that in the interval that I circled from 0 to pi, I know that the purple is on top of the blue. So I can now set up my integral as 0 minus pi of the purple equation minus the blue equation, and then integrate both of them. Integral of sine is negative cosine. And same idea here, so minus becomes plus. But when you do sine of 2x, you have to divide by 2 to counteract the chain rule. And so I'm going from 0 to pi. Let's just use this little space over here. If I plug in pi, then I have -2 cosine pi plus cosine of 2 pi over 2. And I'm going to subtract the answer when I plug in 0. -2 cosine of 0 plus cosine of 2 times 0 over 2. This first chunk becomes positive 2 plus 1/2. Cosine of pi is -1. Cosine of 2 pi is +1. The second chunk becomes -2 plus 1/2, because cosine of 0 is 1. And did I get my 1/2s right there? Yeah, I have my positives and negatives correct. So I have 2.5, which doesn't need to be in parentheses, minus -1.5. And so I get total area of 4. Okay, that's one example. Another example that I was asked about was finding the area between these two curves. And this time I'll start off with different colors. So I've got y equals the absolute value of x, and y equals x to the 2/3. Now, it's kind of hard to maybe think about how these two equations intersect, but you still set them equal to each other. Absolute value of x equals x raised to the 2/3. I know that the absolute value of x is really equal to two different functions, and one of those functions is just regular old x. So if I'm talking about positive values, then I'm really just considering this equation here. And so this is true if x is greater than or equal to 0. But the nice thing that I know is I know that this is symmetrical. It has this sort of a graph. And this is also symmetrical because it has a second power right there. It's going to look something like this, or maybe some other sort of shape like that. But the x squared piece tells me that I'm going to be symmetrical on both sides. It's going to be parabola-ish. Okay? Same as before. If I have terms on both sides, I'm going to subtract to make it equal 0. I'm going to factor out what they have in common. And I'm going to get two different possibilities. X is 0, or x to the 1/3 is 1, which is the same as saying x is equal to 1. Now remember that this is actually a symmetrical situation. So you have like two different regions. You have this region that I drew very badly because they intersect here at 0. And I have this region right there. And they're going to be equal to each other. So the total area can be written like this: 2 times the value of R2, or equivalently R1. The reason I chose R2 is because that is the positive one, from 0 to 1. I need to figure out who's on top and who's on bottom, and that may be a little bit tricky to do, because it could have been that my picture is actually like this, where my curvy function kind of goes like that. It's not obvious which one is on top and bottom, so choose a value that's in the middle of the interval and use that. So I could use, for example, 1/2. If I use 1/2, then this is just equal to the absolute value of 0.5, which is 0.5. If I choose 1/2 is a tricky one because of the divided by 3 in the exponent. I'm going to change my idea to something that can be cube rooted. That's what divided by 3 means. So maybe let's change my value to 1/8. Okay. Now if I do 1/8 as my value here, the cube root of an 8th is a half, because the cube root of 8 is 2. So I have a half. That's dealing with the over 3 power, and then square that, you get a quarter. So it actually turns out that the purple function is on top because it is a bigger value. And that kind of makes sense because the 2/3 power is less than 1, so you know that it will eventually be lower than the absolute value. Anyway, we're going to do purple graph minus, blue graph, and dx. Now, absolute value does not have its own antiderivative because it's two different functions. But on the interval I care about, the absolute value of x is just equal to x. So I just have to do add 1 to each of the powers. So add 3 over 3 divide, add 1, so it becomes 2. And that's evaluated from 0 to 1. So that's 2 times 1 over 5/3 minus 1 over 2. And when you plug in 0, it's all 0 anyway. So this is 2 times 3/5 minus a half. In other words, 6/5 minus 1. I just distributed the 2. And so I guess we get an answer of 1/5. So there's a few examples of finding areas under the curves without a calculator. Please let me know if you got any questions.